Okay, welcome back. This is actually a continuation of question 4. Unfortunately, I got interrupted while I was recording. So we are going to do question 4d now and then move on to 5. So let's do 4d. So this, if you haven't done the rest of 4, could you please see the previous video for A, B, and C. Okay, so 4D, what is the time taken for the radio signal to reach the nose according to those in the spacecraft? Right, this one here will give us a really good understanding of what is actually happening in relativity. So, it's got printing on it. Let's see if I can get a blank. That's better. Okay, so here we are. Let's get our diagram up again. So here is our spacecraft moving forward at 0.7 C, and here is our space station here. Now, according to a person on the actual craft, they think themselves as not moving forward, but they see the space station going back at 0.7 C. They see their craft as 80 meters in length, the proper length. And what is happening is, as these two here are aligning, the signal is sent out. Now, it doesn't matter that the spacecraft, the space station, I should say, is moving backward away from the tip of this craft's nose. Remember, this is where the actual receiver is. The speed of light always travels at the speed of light. So even though the space station is traveling backward at 0.7 C, the speed of light still would have this radio signal going forward at the speed of light. In other words, it wouldn't have mattered if the space station is going back at 0.9, it would still be sending out a signal at the speed of C. Okay? So that simplifies this problem really, really easily, because it says, how long does it take for this signal to simply go from there to this point here where they align? Okay. In other words, how long traveling the speed of light would it take to go 80 meters? So remember, velocity is equal to distance over time. So the time is equal to distance over velocity. It's got to travel 80 meters, and we're traveling at the speed of light. So let's do that. So that's 80, that's 80 over 3 exponent 8, and that is 266.7 nanoseconds, or put that into microseconds, it's 0.267 microseconds. Okay, so that's for C. Okay, right, let's move on to question 5. Okay, question 5 is about muons. Okay, and remember, muons is one of the reasons why we know that the theory of special relativity is actually true. So a muon forms 27 kilometers above the Earth's surface and travels straight down at 0.98 C. From its frame of reference, what is the distance that it has to travel through the atmosphere to make it to the surface of the Earth? Okay, so let's have a look at this. So here is the Earth, and that's the Earth there, and this would be our atmosphere. Okay, and according to the we know that this distance is 27 kilometers, and the muon enters here. Okay, and it's traveling at a velocity of 0.98 C. So what the muon will see is it would see this atmosphere coming towards it. Okay, so if the muon becomes stationary, so we assume the muon is stationary, the velocity here, we assume that the Earth is coming back towards it at 0.98 c. Okay, so from the muon's frame of reference, they think that they're stationary and it's the Earth arriving. So it would see this 27 as being foreshortened. So let's work out what we need. We need LV equals L naught over gamma. So we need a gamma factor for the situation. So the gamma would equal 1 over the square root of, let's move that across, 1 minus 0.98 squared. So the gamma here is 1 over the square root of 1 minus 0.98 squared. It's 5.025. Okay. So no longer does the muon see 27, it's going to see it foreshortened by a factor of 5. So what is that? It's going to be 27 divided by the gamma factor. So it's 27 divided by that number. So it's 5.37 kilometres. Okay. So the muon only thinks the atmosphere is 5.37 kilometres in thickness. So that's A. B. A physicist measures the muon decay after 92 microseconds. How long does a muon take to decay according to its reference frame? Okay. So the B, a muon's proper decay time, so T0, is 92 microseconds. Okay. Do I want the velocity here, or do I want the T naught or TV? And I think that's what TV. Yep. So the dilation is TV equals gamma T naught. Okay, and where is it? I'm looking at question 5. So this is, I just realised that this is actually remembering we're assuming that the muon is stationary. It's the Earth that is moving. So the proper time, this is the time at velocity. So we are actually observing the dilated time. So this is TV. This is my apology. This is why I'm starting to worry. So it was TV is 92. So that's the dilated time. What would the muon think? The muon would be a shorter time, so 92 would equal gamma times T naught. So 92 would equal 5.025 times T naught. And so 92 divided by 5.025 equals 18. T naught is 18.3. Now, remember, units are important here. That was microseconds, so that's also microseconds. So according to the muon, its decay happens after 18.3 microseconds, but we measure it at 92 microseconds because this one here is assuming that it is stationary, and this is what, from its reference frame, is that value there. Okay. Next, how far does the muon travel before it decays according to the physicist's reference frame? Okay. Well, the physicist thinks that it is going to be traveling for 92 microseconds. So for C here, definitely the physicist's reference frame, its velocity is equal to distance over time. So distance is equal to velocity times time. The velocity of this muon is 0.98 according to the physicist, times c, which is 3 by 10 to the 8th, times the time, which is 92 microseconds minus 6 there. Okay. So according to the physicist, it's going to travel 0.98 times 3 exponent 8 times 92 times -6. It's going to travel a distance of 27,048 meters, which is 27.05 kilometers, which is the entire distance of the atmosphere. Okay, let's look at D now. D says, how far does the muon travel before it decays according to its reference frame? Now, in its reference frame, it decays in 18.3 seconds. Okay, and the Earth is moving towards it at 0.98 c. So the distance that it will travel would be the velocity, which is 0.98 times the speed of light. Okay, so that's how fast the Earth is moving towards the muon, multiplied by 18.3 microseconds. Okay, remember, it will decay after 18.3 microseconds. So let's work out what that distance is. So 0.98 times 3 exponent 8 times 18.3 exponent -6. And that's 5380, forget about the 0.2, meters, okay, which is 5.4 kilometers. Okay. So in our reference frame, it will travel 27. In its reference frame, it will only be traveling 5.4 kilometers. Using this information, what does it mean? How does it explain how both observations mean the muon strikes the surface of the Earth? Well, from our reference frame as the physicists, we see it go all the way through the atmosphere, which we think, or in our reference frame, is 27 kilometers. But remembering that the muon doesn't think the atmosphere is 27 kilometers, it thinks that the atmosphere is 5.37 kilometers in thickness, and it has traveled 5.4 kilometers. So in its reference frame, it's traveled through this entire distance before it strikes the Earth, because it will strike the Earth after that distance. So in its reference frame, it will strike the Earth. In our reference frame, it strikes the Earth, because in the two reference frames, this length here and this length here are the same length. They're just the equivalent of each other's lengths. This is the foreshortened, and this is the non-foreshortened. But these two lengths are the same. They're measuring the same distance. That is the thickness of the atmosphere. Okay. And finally, let's do question 6. Question 6 says, a physicist observes a muon decaying in 1.52 microseconds in their reference frame. From the reference frame of the muon, it decays in 1.2 microseconds. So what's the velocity of the muon? Okay, so this is one of those ones where we're working out the gamma factor and we're going to work back to find the velocity. So, question 6. The formula for time dilation is TV equals gamma T naught. Okay, remember, gamma is a number greater than 1. So this, when we look at it, it's 1.52 microseconds equals gamma times 1.2 microseconds. So this is the time, the dilated time is 1.52 in this question, and the non-dilated time, or proper time, is 1.2. The units have to be the same to cancel on both sides. So that gives us gamma equaling 1.52 on 1.2. 1.52 divided by 1.2 gives us 1.26 repeater. I'll just put a few there in sevens. Okay. Now, if we didn't get a gamma being greater than 1, we would have got these in the wrong position. So now using gamma equaling 1 over the square root of 1 minus the coefficient of light speed squared, we'll use that formula there. So 1.2666 dot 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 equals 1 over the square root of 1 minus k squared. Swapping them over and squaring, 1 minus k squared would equal, so I'm going to reciprocate that and then square it. So 1 minus k squared would be 0.6232, so on. 1 minus that answer, k squared would equal 0.3767, and finally k is equal to 0.6137. Therefore, we are travelling at 0.61 c, 61% of the speed of light, or 1.84 by 10 to the 8th meters per second. Okay, we'll call this video here. It's gone long enough. And all we'll be going back to do is questions 7 and 8 in the next video. Thank you.